Yeah. Thank you for coming to the class today. Today class is like half. I will talk a little bit more in terms of like explains what is HAZOP, because HAZOP itself is a very important tools that most of the chemical or petrochemical or biochemical industries are using even until today. So it is very useful for all of us to understand how do we construct a HAZOP table, or how do we just run the whole process of the HAZOP analysis. That is why I'm going to do a bit of explanation. And then after that, I'm going to break you up into groups to do some exercise. Yeah. Then on Friday, we will do our normal, what's that called, the tutorial classes. Okay, so HAZOP process base is not individual, so we can't really do HAZOP individual. So even sometimes in the exam, I may give you a question to ask you to do a simple HAZOP. That one I will expect you to just being able to do a very like minimal part of it. But a complete HAZOP analysis require a team. And this team shouldn't be, how should I put it? Shouldn't be confined only to engineering. It should be open up to different individual, meaning you want people from, if let's say, for example, if you work in an industry, in the production line, and you want yourself as a productions or process engineer, you would want your production supervisor, or even you may select one or two operators who run that process itself to be part of the HAZOP team. Then you also want people from perhaps the planning, the scheduling, so that they know, and you know what happened if you have a delay in your schedule, what will be the impact. So you want someone from non-engineering or non-technical like scheduling. And also you may want someone from totally fresh, like have no idea what's going on in the process, but still within the company. I'll give you an example, maybe someone from HR, or someone from finance, or someone from sales and marketing, that they have really no idea how the process is run. The reasons that we pick people from different background and have huge differences is so that we have ideas. Again, these go back to our always what we always say, the CDIO concept, but HAZOP is focusing more on brainstorming. That's why we want people from different background. Let me just write it down, and expertise, and we focus on brainstorming. Okay, and of course this HAZOP analysis require a few things. It's not just like what we have done so far, like our CDIO, we have all those concepts like random words and all that, but this one, no, this one is a structured brainstorming. We use guide words to guide us how to brainstorm from one sections to another. Okay, so yep, that's HAZOP. And what are really HAZOPs? It helps us to analyze the plant or the process. Okay, so most of the time HAZOPs are done before the process is being designed, and also during safety review, meaning your process is running up and running. Every 3 to 5 years, we will actually review HAZOP. Means every 3 to 5 years, if it depends on company. Some company will say 3 years, I don't want a HAZOP, because HAZOP require a lot of manpower, because you need to sit down. Maybe you will spend even up to like 2 or even 2 days to 1 week or even 2 weeks to really do a complete HAZOP analysis. So some company will say, oh, I can't afford that manpower. So they will only want to do it once every 5 years. Some company, they will say, every 3 years, I will do a minor HAZOP, maybe just focus on 1 or 2 process. And every 5 years, I will do a major review. Okay, so it's up to the company. But it helps us to see what are the possible deviations for the design, with what are the consequences, and what are the safety the operations concerns and also the environment concern in here. And HAZOPs are only done on processes, by the way. You can't do HAZOP on human. You can't do HAZOP on certain things, yeah? It's only for a chemical processes that has flow, the process flow. And they must have the process conditions, meaning when we do HAZOP, okay, we need certain things. We need your process flow diagram. If you do not have a process flow diagram, means that process that you're looking at may not be suitable for a HAZOP review. Perhaps you may want to start with drawing a simple process flow diagram first. And after process flow diagram is different from PNID, yeah, by the way. Process flow diagram is where, let me just scribble here. It's like you have storage, okay, go into mixer, and so storage A, and then you have B, go into mixer, then you have reactor, and then you have separations process 1, and it go up and down. So this is what we call process flow diagram, means it's a block diagram. Yeah, I believe we are learning them now. Together with your process plant design, we talk about process flow diagram, and also in your material and energy balance in your year 1 or year 2, we talk very much on process flow diagram. Okay, so it's basically the block diagram, but it will help you to be able to do at least your basic M&E, your basic material balance. So whatever input here, whatever coming in, or your input, or your in 1, in 2, and your output here, all of this must be balanced. Okay, that's one part of process flow diagram. Okay, so the next one that you need, okay, why is this not coming up now? Okay. Okay, so other than process flow diagram, you need your PNID. Okay, you know what is the difference between process flow diagram and PNID right now, right? PNID is where you have your instruments itself, where let's see if I will have a PNID here. Okay, I have, but later I'll show it to you here. Okay, then you need your equipment specifications, tells you about like what materials that your reactors using, what materials your mixer is using, and HAZOPs, when we do HAZOP, we have to identify which one we want to work on. Okay, so you need to have all this data ready. You need to know what is the material constructions of your equipment. Okay, and then of course, as I mentioned, you need your M&E balance, which this and this go hand in hand. Okay, so how do we start? Okay, so for HAZOP, one thing is we want to break things into different unit numbers. For example, reactor, storage. So if let's say when I look back in here, so you will have to split your team. Okay, so SDS come later. SDS is not required in HAZOP. Okay, HAZOP is a safety review. So we will look at storage here. Perhaps this is number 1. We normally will number our big chunk of our process itself. Like reactor, we'll say, okay, number 3. So most of the time we'll start with the scariest one. The one that will likely run away, which in a lot of time is our reactor or our distillation column. Yeah, so it's either our reactor or our separator. So if you do not have a HAZOP in the plant at all, the first thing we look at, we will go for the highest, the highest risk one. In this case, it will always be reactor, followed by your separations process. The reason because separation process come after reactor is that separation process normally use high pressure and high temperature. Same with reactor. And reactor is a bit tricky because beside high temperatures and high pressure, you have reactions also. It also depends on your reaction. Is that exothermic reactions or endothermic reaction? That itself play a huge role. So that makes reactor as number one priority to work on. Number two is your separations. Mixer, storage, this one, when we have complete all of this here, then we will look back maybe this one as number three, number four. Number three here, number four here, for example. Okay, so let's not confuse us. So today we are going to focus on, the example will focus on the reactor itself. Okay, so then you need to label, means you need to say, okay, I'm looking at reactor. Then you want to choose a study node, like where do you want to study? When I say study node, later we are going to go into detail with this, then you'll see what's the difference. Okay, then we talk about the design. We pick your process parameter, like what parameter you want to study. Like even in a reactor itself, okay, I'm going to draw a quick, ugly, what should I call that? PNID diagram or unit operations diagram. So you have your incoming, you have your outgoing, and perhaps you have your gas venting here, you have your product here, and then you have your cooling water here and cooling water out. Okay, so you have your material in and your product here and gas. Okay, so there are so many things we can study. You can do, okay, I want to do flow. I want to do flow rate of my incoming material. I can do flow rate of my products, or I can do flow rate of my cooling water. You can work on level. It means this one, if it's partial, if you have dual phase in here, you have liquid and gas phase, then you may want to look at level. If not, most likely it's only one. Then you can look at temperature. What is the temperature in here, your reactor? Or you can look at your temperature of your cooling water out. And you can also look at your temperature of your incoming material. So there are many things that you can look at that you can pick. So that's the tricky part. As an engineer, which one do we go for? As I mentioned, first, we always go with priority. Like when we select reactor, we know because reactor has so many things to look at. So again, when we choose the parameter, we will have to see, okay, which one will give the worst case scenario? In this case, I will say if it's a reactor, I always start with pressure, okay, or temperature. Okay, pressure and temperature always go hand in hand because when you have high temperature, you have high pressure. It's just like when you have high temperatures, your liquids or your chemicals will easily vaporize, and that will result in higher pressure. So you can work on temperature or you can work on pressure. That will be the number one to work with. Then number two, perhaps you may want to work on flow. Or if you have a few different temperatures to work with, you may want to work with your reactor temperatures. The second one, you want to work with your cooling water temperature. Then you go into your flow. So it's again, there's no right or wrong way to do this. As an engineer, we decide which one is important for us to work on. Okay. So that's that. And then after that is where HAZOP really began, that you choose the word. And what is all these guide words? I'm going to show you in a while. And so deviations possible. And we are going to go into this in detail. So you don't have to worry about number 5, number 6. But choosing a design is important. Which one to study, where to study, what to study, and why do you want to study them? So priority is, you need to prioritize. And yeah, that's it. Okay, so let's skip all this because we're going to jump into the doing part of this. It's easier to do it together than to read this one by one. Okay, so just now I mentioned guide words. Yeah, so just give an example. Guide words here, we have a simple one: no, not, non, higher, greater, lower, and less. Well, what do we mean? What do we mean by this? Let me show you an example. Okay. So when we have just now we say we want to work on temperature, for example. As our parameter, yeah, this is our process parameter. And perhaps we look at reactor temperature. Let's be more specific. Okay, so then we choose our guide word. So when we have temperature, what does it mean that when there's no temperature, does it work? So meaning if there is no temperature, that doesn't make sense, because no matter what, we always have a temperature there. Okay, when there is no temperature, there's only shows one thing. Our controller, our temperature sensor or our display is 40. So then you just change that. You don't need a HAZOP to run temperatures when there is no temperature. Okay, so no doesn't apply here, because when we say no temperature means you just change one of whatever is 40 there. So what happened if we say we have higher temperature? So if your reactor, remember just now we mentioned that you need to know what is your process condition. So if we are supposed to run at 200 degrees Celsius, for example. What happens if now you look at, hey, my temperature display tell me I'm currently running at 300 degrees Celsius. What does that mean? What went wrong? That's where then you know, okay, something is not right with my process. And what are the possible things that can go wrong with higher temperature? Possible is my cooling water is not working. I have perhaps if I have a stirrer, then maybe my stirrer is stirring too fast, generating heat and causes the reactions to be more rapid. And it could be something else, okay? Or my cooling water, perhaps the cooling water is supposed to come in at 20 degrees Celsius, but it came in at maybe like 100 degrees Celsius. It doesn't cool enough. Okay, so there are so many possibilities. Okay, so what happened if you're supposed to run at 200, but now you look at it, the display shows 50 degrees Celsius. What could go wrong? What could cause your reactors now at 50 only? You may want to look at, oh, perhaps I have contaminations in my material. Maybe my material is not reacting. Therefore, there's no exothermic reactions. Or maybe my stirrer is not working, so there is no mixing of chemical. Maybe my cooling water, someone goes to change the accidentally open up to a maximum flow for my cooling water, supposed to come in at a certain flow rate, but now it's at full blast and it cool down the reactor too much. So there are possibility of things that can go wrong. So we know greater, you can use either more temperature or higher temperature or greater temperature or lower temperature or less temperature, it doesn't matter. So these are just words that help us to think, to start thinking, okay, what could go wrong? What could cause this? Okay, make sense now? Any questions about why do we use guide words and what are the guide words for? Anyone? Any questions? If not, then I'll just go to more and more guide words. So as well as we are looking at temperature, right? Can temperatures be as well as? No. As well as most of the time is it is when we have something that not supposed to happen, but it happens at the same time. For example, we're supposed to have product A and product B that go into the reactor, but but that is also another line that is supposed to close, is for cleaning only, but someone turn on the valve and the water come in. So you have besides your A and B, then you find out some funny elements in there. That is when we use as well as. So most of the time is on chemical compositions or something that involves streams, involve flows. Okay, part of. So it's always qualitative decrease. Some of the design intentions are not achieved, some are not. Is like part of can be used like when we look at our product. Okay, when you have A plus B give you C plus D. Okay, and C plus D is here. Okay, but when you check, you're supposed to have like 70% C, 30% D, but you only have perhaps 20% here, 10% here, and then you have A and B in here. That's where your part of come in. Okay, so you may want to again check back your reactor, what went wrong. Reverse, most of the time talks about flow. Okay, it's mainly about flow or chemical reaction. Okay, so you can have a reverse flow or you can have a reverse reaction. So this guide words is only used for specific parameter. Okay, other than is some things like completely constitution. Just now we say as well as you have A plus B as well as water. Okay, but now it's like you're supposed to have A plus B, but A doesn't exist. You have B plus water. So meaning it's completely being substituted, or someone make a mistake in the storage area. They are supposed to store A, but somehow they pour in C in the storage tank, and so you have B and C in here. Okay, so all the things that can go wrong, you will have to brainstorm and then see how did that happen, what is the consequences when that happens. Okay, but these keywords will help you to start thinking like okay, that might be something wrong with the storage area, so what actions can I take, or what actions can my operator take if I'm sleeping? That happens at 2 a.m. and the operators look at that composition and say, oh no, I have something funny in here. What do they need to do? HAZOP will tell them what to do. Okay. So that is why it is important to have a very good HAZOP so that people know how to react. When any of this scenario happens, they know what to do. Okay, because later on, we're just brainstorming of what could go wrong. And after we brainstorm what could go wrong, then the next part is what actions can we take to counter that? Or what preventions can we do to even prevent that? Okay, so now we have other than, we have sooner than most of the time is talking about timing. 3 a.m. or 3 p.m. is supposed to change chemical, but you realize that your chemicals start coming in at 1 o'clock. Or later than is supposed to come in at different at 3 o'clock, but it came in at 4 or 5. Okay, or it's supposed to A come in first, then followed by B, but B come in first, followed by A. So these are all the possibility that you can play with these guide words. And where else it's supposed to come here, but you have been waiting there, but your chemical A and B doesn't come in. Maybe they connect the wrong hose, or they have so many piping there, they may have off some valves along the way and it went somewhere else. Okay. So these are the primary keywords or process parameters that we will look at. These are the flow, temperature, pressure, level, and so on. So most of the time as a beginner level, I would say, as you grow, as you become more and more experienced as an engineer, as a process engineer, as a productions engineer in the future, you realize that you will add in more and more process parameter in there. But as a start, when you do not know what to do as a fresh engineer, if you do not have a senior to guide you what to look at, always go with the basic flow, temperature, pressure, level, composition. This will not go so. Will never go wrong. Okay, so the rest is more, I would say, a little bit higher level. Okay, require experience in the process, require knowledge in the chemical reactions and all that for you to look at other, like all of this. Okay, any questions so far? Okay, so this is just a summary table. Let's jump into what we want to do. Okay, assumptions here. So most of the time, HAZOP analysis is brainstorming, means is like something that has not happened before, but we are thinking what might go wrong. So you need a very strong, as I mentioned just now, you need a team that is from different background. You need someone that is practical, that's hands-on, like your operators, your line supervisor or line leader, and yourself as an engineer, or you may even need the technicians or the maintenance guy who understand the process. And you also need someone from different background, or even you may need someone from the management team that can make management decisions to say, okay, if I need to come up with budget to change this, that they can make the call and say, yes, we're going to change that. You need someone that has the power to say, yes, we have the money, we can buy this, we can make this, we can do this, etc. So you want a strong team so that whatever assumptions you made in your HAZOP analysis, whatever actions required to take is valid. It is something that can be doable. Okay, if not, then this HAZOP is useless. Okay. So HAZOP table or form looks, a complete one, a professional one looks like this. I'm going to stop sharing here. Okay. And so I'm going to start sharing on my, okay, hold on, this one. And also I will give you all the link for this one. Okay, I'm going to put this in the chat box, the link here. So I believe you all have it now. Okay, you can go to this link, and then this is the example that we will be looking at. This is actually the classroom example. And of course, if you look at my slides, some of them you already have the answer in there. But we are going to do something that is not in the answer so that we can do completely different things. Okay, so let's take a look at this one. I only see 3 people in here. So come jump into this Google spreadsheet that is in the link here. So we have, let me see, what can I do here? I want to draw. Where's my drawing tools? Oh dear, I don't have the drawing tools here. Okay, now mine. So you can see there is a reactor here, a simple reactors, as what I simply sketched just now. We have our monomer feed that feed our incoming, okay? And then I think, yeah. And then we have our cooling water into the cooling coil. We have our stirrer in here, and we have a thermocouples to look at if, let's say, the temperatures go too high, it will adjust the cooling water flow rate. Okay, and of course down here, which I think accidentally cut it off, the reactor bottom here is where the output, the products, where it goes out. Okay, so yeah, so this is where our products the whole things look like. So how many of us here? We only have 5 in here today. Where is your classmate? What happened to the rest of them? Okay, in that case, we're just going to do a quick one. I think we can't do too many. Okay, my notes give you the cooling coil HAZOP, so you can refer to that and how that is being done. So what we will do is we'll do the stirrer one. Okay. So what could go wrong with the stirrer? Yeah, so we go to the second tab. Okay, so process parameter here is just your stirrer, means there's only one thing that we can do, RPM for our stirrer. Okay, let me just copy and paste this here. Okay. Copy and paste. Okay. So we have RPM here. And so guide words can be what happens when it's too fast or too slow. The second one is too fast. Okay. And because RPM means the spinning speed, what happened when there's no speed, no RPM. I think that's about it. Anything else can we work with this area? Not really. Okay, so what are the possible causes? We are just going to look at one or two. What are the possible causes that causes our stirrer to go too slow? Anyone? You can actually fill it up. You don't have to wait for me to fill up. If you have idea, you can just pop it in. I'll leave it to you all. Are you still here with me? 40 wire. Yes, that's a good one. Insufficient power. Yes. What about too fast? I will say wrong setting. Someone may have accidentally set it to a different setting. Okay. So we are just going to look at two. That's enough. Then since there's only 5 of us, I think that once you'll get the concept, then we can release the class, because I just wanted to focus on how we can do a simple HAZOP. And for your information, HAZOP is always, let me not record this. Where's my recording? So we look at consequences. We only need 1 or 2 consequences that is really impactful when we do not have when we have this slow RPM. So slow RPM, insufficient power, we may have our incomplete reactions, we have low production yield, and then when it goes to the next process, it may actually causes hiccups in the next process, because it was supposed to expect C and D products that go in, but now we have A and B, C and D in there as well. So it actually becomes a more complications separation process for the next step. Okay, so that one we put it here. So what sort of actions do we require in here? Okay, so actions here, you can take it against your consequences. You can take it against your possible cause. Okay, and also actions has 2 types. One is detections. How do you detect that? And one is prevention. So let's start with detection first. Detection is always the easiest. So when you have too slow, you can have a what we call that, the alarm for low or high RPM. So this will cover both too slow and too fast. Okay, that's the detection. Okay, so any other detections method? Okay, and also you may want to have a check gate for your to know whether you have a incomplete reaction. So you may want to have a sensor, what's that called, the chemical ratio or composition sensor at the reactor to check the reactions process. Okay, so that again is a detections because we put in a sensor to tell us, okay, this one can go, no go, etc. Okay, so this is detections. What about prevention? And also, how do you want to detect insufficient power of faulty wire? So when you have insufficient power, how do we want to detect that? Is there any way we can check that? It is okay if, let's say, there is none. Anyone? You can unmute yourself to say if you can think. If let's say we can't think of anything, then we would just continue. So we have the detections here. Then now we want to talk about prevention. Okay, so preventions. How do we want to prevent insufficient power? Can we prevent that? Perhaps no, because insufficient power a lot of time, it really depends on your motor. Is the insufficient power can be your incoming of your electricity. That one we cannot prevent. But if it's the motor, if it's for insufficient power in motor, perhaps it is because of old OH, then we will need preventive, or we call it scheduled maintenance, to change that, to change or repair the motors. Okay, so that's one. Anything else? So preventive maintenance is very good way to look at all this. Faulty wires, that's only repair. Okay, so if there's a faulty wires, immediately you want to, that's the actions for faulty wire. To get electricians to change that. Okay, so that's actions. That's not even preventions or detection. It's just an actions that you need to take. So here we have D means detections. For detections purposes, we have preventions, means we will schedule it to change or to repair the motors or to service the motors on every few months. We are going to talk more and more about all this, like preventions and all that, in the later chapter, but this one is just allow us to like look at, okay, what are the actions that we can take? Okay, so if that's it, then we are done for too slow. Okay, so then too fast, perhaps wrong setting. And if wrong setting, what are the possible consequences? Means we have heat generations, additional heat generation, sorry, that can causes higher reactions temperature, which is something that we want to avoid. So but this one's most of the time, because you see we have a thermocouple here. If temperatures goes up, most of the time the cooling water, this is where we say is part of the prevention, the control, the thermocouple control system, increase or adjust the cooling water, flow rate. Okay, that is one of the preventions. What else? Perhaps the second prevention is wrong setting. It could be some operators accidentally change it, or it could be someone's forgot about it. So of course, when it is too fast, again, we have the detections earlier, we have the alarm in there. You do need to repeat that. So you can just move on with something that you have not written before. So what else can we put in? too fast, wrong setting, perhaps you may want to do a safety lock to prevent unauthorized personnel to change process setting. Perhaps that's another way to prevent it. Okay, so you can see what I wanted to put up here is that these guide words help us to think what could go wrong with the parameter. Okay, so you put down the possible causes here, and then we see like what are the way or actions we can take to prevent these causes to happen, or to detect these possible causes from happening. Okay, this is how we set up our system, because before that you may just set up a bare systems that has no interlock, has no locking of any form in here. It's just a bare process system. But with a good HAZOP, you will notice, oh, I need an alarm. So you will put in a temperature sensor, you will put in an RPM detector, you'll put in a pressure sensor, and that's where it helps you to build your PNID as well. Okay. So when there's no RPM, we can say Moto 40 is what I can think of. Possible consequences is again incomplete reactions. It can be repeated, but if let's say the things is repeated, you can just copy and paste in here. Okay, so again, because this one and this are similar, we will just use back the same thing. You can just put refer to item. So most of the time we will put something like that, 1, then 2. So if you notice HAZOP, they always like to put numbers in front so that we can say refer to which one. So this is number 1, then it will be 1.1 or 1.2. Okay, and so this is 2.1, and this is 3.1. And so, and all this, perhaps this is 1.1.1, okay. So refer to item 1.1.1. You can just write that. It is allowed in HAZOP. Okay. That's it. We have done a simple HAZOP analysis. Of course, a comprehensive HAZOP analysis, you can see this whole thing can build up. It can slowly, if we do it correctly, because we're only looking at one parameter in here, one equipment in here. So imagine when you complete with your reactors, and then you move on to your separators, and then you move on to your mixer, you move on to your storage tanks and all that. At the end of the day, you will have a complete HAZOP handbook. I call it handbook because you may end up in a 3-inch arch file, or you may end up with like 10 or 20 tabs in here in an Excel sheet, and each one of this line will go down to thousands of lines. Okay, and that is allowed. Okay, because this is how we look at what could go wrong. Then we want to prioritize. We start to say, okay, this is important, we will have to do this first. This is not important, this one may happen, may not happen, then we can put it aside first. But you know, when anything happens, when anything goes wrong, you can always refer back to this handbook, the HAZOP handbooks that you and your team created. Okay, any questions so far? Class? If not, I think that's about it for what I wanted to show you all today. Let me see my notes. Yep. That's it. That's what I wanted to mention for today, just to prepare you how to do HAZOP. And then Friday, we are going to look at our tutorials. Friday tutorials. Let me see, just a quick one. So tutorial on Fridays will be more on discussions again, if I'm not mistaken. Yes, hazard identifications, we talk about study notes, we are talking about robots, okay, humanoids, robots, and we will be talking about some things that could go wrong. Okay, so there will not be any HAZOP studies on Friday, maybe a quick one, maybe just question one. I think that's one for HAZOP study, just to prepare you all again to do it on your own, a quick one. And then the rest will be more on discussions. We're going to do it like I'll pass recording today's 2 times. Okay, I'll do that. Thank you for reminding me. Sorry that I didn't upload last week tutorials, and I'll do it after this. Okay. So any questions so far? If no, then I'll see you on Friday. We are for the Friday tutorial. Then all the best in your test next week. Okay. See ya. Bye bye.